In today's documentary, we will discuss everything you need to know about quantum mechanics. Let's begin. By the year 1800, physics was in an extraordinary position. It had, for all practical purposes, solved the universe. Isaac Newton had given the world 3 laws of motion and a law of universal gravitation that could predict the path of a cannonball, the orbit of a planet, and the trajectory of a comet with stunning accuracy. James Clerk Maxwell had unified electricity and magnetism into a single, elegant framework and shown that light itself was an electromagnetic wave. Thermodynamics had been worked out. The behavior of gases had been understood statistically. Everything seemed to fit together into one coherent picture of reality. A universe made of matter and fields, governed by precise mathematical laws, operating like an enormous clock that could, in principle, be wound back to the beginning of time or forward to its end, if you just knew the starting conditions well enough. The physicist Lord Kelvin, standing at the close of the 19th century, reportedly said that physics was essentially finished, and that the only work left was to measure things more precisely. 2 small clouds, he said, remained on the horizon. He believed those clouds would dissolve once the right small adjustments were made. He was catastrophically wrong. Those 2 small clouds were not small adjustments. They were the complete destruction of everything physics thought it knew about the nature of reality. The first cloud was the failure to detect the ether. The second was the behavior of something called blackbody radiation. Let us focus on the second one, because that is where quantum mechanics was born. A blackbody is a theoretical object that absorbs all electromagnetic radiation that hits it and then radiates it back out. In practice, a small hole in an otherwise sealed container comes very close to behaving like a perfect blackbody. Heat the container up, and light of various frequencies comes out of the hole. The question physicists were trying to answer was, what is the distribution of frequencies in that radiation? In other words, if you heat an object to a certain temperature, exactly how much energy comes out at each wavelength of light? This seems like a purely technical question. But when the best mathematical tools of classical physics were applied to it, the result was a disaster. The classical prediction was worked out by John William Strutt, better known as Lord Rayleigh, and James Jeans. Their formula, derived carefully and correctly from the accepted principles of the time, said that as the frequency of light increases, the energy radiated should increase without limit. Bluer light should carry more energy than red light. Ultraviolet light should carry more energy than blue light. And the energy should keep climbing infinitely as frequency climbs. This meant that a heated object should radiate an infinite amount of energy, almost entirely in the ultraviolet and beyond. Just sitting next to a warm stove should expose you to an infinite blast of high-frequency radiation. Obviously, that does not happen. Objects glow red, then orange, then yellow, then white as they get hotter. They do not explode into infinite ultraviolet energy. This catastrophic failure of classical physics was eventually called the ultraviolet catastrophe. It was not a small discrepancy between prediction and observation. It was an infinite error. Classical physics was not slightly wrong about blackbody radiation. It was infinitely wrong. The experimental data was clear. At low frequencies, the classical prediction worked well. But at high frequencies, instead of continuing to rise, the energy in the radiation dropped sharply back towards zero. The universe was not radiating infinite energy. Something was cutting off the high-frequency modes. Something was preventing energy from piling up at short wavelengths. And no one had any idea what that something was. Into this crisis stepped a man who did not want to revolutionize physics. He just wanted to find a formula that fit the data. Max Planck was a conservative man. He was not a revolutionary by temperament. He believed deeply in the power of classical physics and had spent much of his career trying to find a rigorous thermodynamic derivation of the laws of blackbody radiation. He was methodical, careful, and deeply committed to doing physics the right way, starting from established principles and deriving results through careful mathematics. By the year 1900, he had been working on the blackbody problem for years. He had made some progress, deriving a formula that worked well in the low-frequency regime, consistent with the Rayleigh-Jeans result. He also knew of a separate empirical formula, derived by Wilhelm Wien, that worked well at high frequencies but failed at low ones. Neither formula worked across the full range of frequencies. In October of 1900, Planck was handed fresh experimental data from colleagues at the Physikalische Technische Reichsanstalt, the German National Institute of Physics. That same evening, in what he later described as one of the most intense intellectual experiences of his life, he found a mathematical interpolation between the two formulas. By guessing at the right mathematical structure and adjusting two constants, he constructed a single formula that fit the experimental data across the entire range of frequencies. It worked perfectly, immediately and completely, not approximately, exactly. But Planck knew that a formula that fits data without a physical derivation is just curve-fitting. It tells you nothing about why the universe behaves that way. He needed to understand where his formula came from. He needed a physical explanation. What followed was, by Planck's own account, an act of desperation. To derive his formula from first principles, Planck had to make an assumption. He assumed that the electromagnetic oscillators inside the walls of the blackbody, the tiny vibrating charged particles that absorbed and emitted radiation, could not exchange energy with the radiation field in a continuous way. They could only absorb or emit energy in discrete, indivisible chunks. He called these chunks quanta, from the Latin word for how much. Each quantum of energy was proportional to the frequency of the oscillator's vibration. In words, the energy of a single quantum equals a constant multiplied by the frequency. That constant is now called Planck's constant, and it is one of the most fundamental numbers in all of physics. Written in symbols, it is the letter H, and its numerical value is approximately 6.626 times 10 to the power of negative 34 joule seconds. That is an extraordinarily small number. It is 0.000 and then 33 more zeros, before you get to the digits 6626. Planck's constant is small in the same way that a single atom is small compared to a human being. It is so small that at the scale of everyday human experience, it is completely invisible, which is exactly why we never notice quantum effects in our daily lives. With this assumption, Planck derived his formula perfectly. The math worked out in a completely self-consistent way. The reason the high-frequency modes were cut off was now clear. High-frequency oscillators had high energy per quantum, and at a given temperature there simply was not enough thermal energy available to create even a single quantum at the very highest frequencies. The quanta were too expensive, energetically speaking, so those modes sat empty, and the total energy stayed finite. The ultraviolet catastrophe was resolved. But Planck was deeply uneasy. He did not think he had discovered something true about the nature of energy. He thought he had performed a mathematical trick, a calculational device that happened to give the right answer. He spent years afterward trying to find a way to derive the same formula without the quantization assumption, hoping he could show that the discreteness was a mathematical artifact rather than a physical reality. He never succeeded, because quantization is not a mathematical artifact. It is a feature of the universe. And the person who made that absolutely clear was not Planck. It was a 26-year-old Swiss patent clerk who was thinking about something else entirely. In 1905, Albert Einstein published 4 papers that each, individually, would have been sufficient to make a scientist famous for life. One of those papers explained Brownian motion, the random jittering of tiny particles suspended in a fluid. One introduced the special theory of relativity. One contained the equation energy equals mass times the speed of light squared. And one, the one that would actually win Einstein the Nobel Prize in 1921, explained the photoelectric effect using a radical extension of Planck's quantum idea. The photoelectric effect had been known for years. When you shine light on certain metal surfaces, electrons are knocked out of the metal. This seems unsurprising at first. Light carries energy. Electrons are held in the metal by electrical attraction. Enough energy should be able to knock them loose. But the experimental details were deeply weird, and they made no sense under classical wave theory. First, the energy of the ejected electrons did not depend on how bright the light was. It depended on the frequency, the color of the light. Dim blue light ejected electrons with the same energy as bright blue light. Bright red light ejected no electrons at all, regardless of how intense it was. Second, there was a threshold frequency below which no electrons were ejected, no matter how intense the light source was or how long you waited. Third, when electrons were ejected, they appeared instantly, with no measurable time delay. Classical wave theory predicted exactly the opposite of all of this. Waves carry energy spread out over their entire wavefront. A very bright wave carries a lot of energy. A very dim wave carries a little energy. Given enough time, even a very dim wave should deposit enough energy to eject an electron. And the color of the light its frequency, should not be the determining factor. The intensity should be what matters. But that is not what happened. Einstein looked at this problem and made a move that was even more radical than Planck's. Planck had quantized the energy of the oscillators in the walls of the blackbody, but he had left light itself as a continuous wave. Einstein proposed that light itself was quantized. That light was not a smooth, continuous wave, but was made of discrete packets of energy, individual particles that he called light quanta, and that we now call photons. Each photon carries an energy equal to Planck's constant multiplied by the frequency of the light. High-frequency blue or ultraviolet light means high-energy photons. Low-frequency, red or infrared light means low-energy photons. And when light interacts with the electrons in a metal, it does so one photon at a time. One photon hits one electron and either transfers enough energy to eject it, or it does not. This immediately explained everything that was puzzling about the photoelectric effect. The reason a minimum frequency was required was because each photon had to carry at least enough energy to overcome the binding energy of the electron in that particular metal. Below the threshold frequency, each individual photon was simply too weak, regardless of how many of them there were. The reason brighter light produced more electrons, but not higher energy electrons, was because more photons were hitting the surface, ejecting more electrons, but each individual electron still received exactly the energy of one photon. The reason there was no time delay was because a photon either hits an electron or it does not, and the interaction is instantaneous at the quantum level. The explanation was elegant, simple, and completely irreconcilable with the established picture of light as a continuous electromagnetic wave. Because Maxwell's equations described light as a wave. Young's double-slit experiment had definitively shown that light was a wave. The interference patterns, the bright and dark fringes, were unambiguous proof of wave behavior. And now Einstein was saying light was made of particles. Both could not be true, and yet both were true. This contradiction, wave and particle simultaneously, would become the central mystery of quantum mechanics, and it would refuse to resolve itself no matter how clever the physicists became. Einstein's paper also contained a prediction. The maximum kinetic energy of an ejected electron, written in words, equals Planck's constant multiplied by the frequency of the light, minus the work function of the metal. The work function is the minimum energy needed to free an electron from that particular metal. This linear relationship between frequency and maximum electron energy was a clear, testable prediction. It took more than a decade to verify it with precision, because the measurements were extraordinarily difficult to make. Robert Millikan, who was deeply skeptical of Einstein's photon idea, spent 10 years designing and performing meticulous experiments, specifically trying to prove Einstein wrong. In 1915, his results confirmed Einstein's formula exactly. Millikan was reportedly unhappy about this. He had proven a theory he believed to be physically absurd. But the data did not care about his intuitions. The data cared about what was true. And what was true was that light, The thing Maxwell's equations described as a continuous wave was also made of indivisible particles. If this was true for light, maybe it was also true in the other direction. Maybe things that everyone assumed were particles had wave-like properties too. That idea would come not from a senior physicist, but from a French aristocrat writing a doctoral thesis. Before we get to wave-particle duality in its full form, we need to talk about atoms. Because by the early 1900s, the structure of the atom had become a serious problem. And understanding how quantum mechanics solved it is essential for understanding everything that comes after. In 1911, Ernest Rutherford performed a landmark experiment. He fired positively charged alpha particles at an extremely thin gold foil, and he measured what happened to them. The prevailing model of the atom at the time, proposed by J.J. Thomson, pictured the atom as a diffuse blob of positive charge with electrons embedded in it like raisins in a pudding. On this model, the alpha particles should have passed through the foil with only minor deflections. Most of them did, but some of them bounced back almost directly toward the source. Rutherford later said this was as surprising as firing artillery shells at tissue paper and having them bounce back and hit you. The only explanation was that the positive charge in the atom was not spread out diffusely, but was concentrated in an extremely tiny, extremely dense core, what we now call the nucleus. This picture, a tiny positive nucleus surrounded by orbiting negative electrons, is the Rutherford model. And it looks intuitive to us now because we have seen it so many times. But it had a catastrophic problem. According to Maxwell's equations, an accelerating charged particle radiates electromagnetic energy. An electron orbiting a nucleus is constantly accelerating toward the center, changing direction continuously. This means it should be radiating energy constantly, losing energy. And as it loses energy, it should spiral inward, faster and faster, crashing into the nucleus in less than 1/10,000,000th of a second. Atoms should not be stable. Everything should collapse. Matter itself should be impossible. And yet, atoms are stable. Hydrogen atoms have existed for billions of years without their electrons spiraling into the nucleus. In addition to this stability problem, there was the problem of spectral lines. When you heat hydrogen gas until it glows, and then pass that light through a prism, you do not get a continuous rainbow of colours. You get a series of sharp, bright lines at specific, precise frequencies. Red at 656 nanometers, blue-green at 486 nanometers, violet at 434 nanometers, and several more, each at an exact frequency, with nothing in between. This pattern of spectral lines was highly reproducible and unique to hydrogen. Every element had its own characteristic spectrum, like a fingerprint. But classical physics had absolutely no explanation for why only specific frequencies appeared, or why those frequencies were the ones that were. Johann Balmer, a Swiss schoolteacher with no formal physics training, had noticed in 1885 that the frequencies of hydrogen's visible spectral lines fit a simple mathematical formula involving integers. The formula was strikingly precise, but it was purely empirical. No one could explain why integers should appear in the frequencies of light emitted by a gas. In 1913, a young Danish physicist named Niels Bohr proposed a model that, while ultimately incorrect in its details, captured something genuinely true about the quantum world and gave physicists their first coherent picture of the atom. Bohr's model was built on three postulates, and they were radical. First postulate: electrons in an atom do not orbit the nucleus at any arbitrary distance. They can only exist in certain discrete orbits, each corresponding to a specific energy level. While in these orbits, they do not radiate despite their acceleration. The rules of classical electromagnetism simply do not apply inside the atom. Second postulate: the allowed orbits are those in which the angular momentum of the electron, a quantity related to how fast it moves in its circular orbit and how far it is from the nucleus, is a whole number multiple of Planck's constant divided by 2 times pi. This quantization condition is what selects which orbits are allowed and which are not. The orbits are numbered by an integer, starting with 1 for the innermost orbit, and that integer is called the principal quantum number. Third postulate: when an electron jumps from one allowed orbit to another, it emits or absorbs a single photon whose energy is exactly equal to the difference in energy between the 2 levels. The photon's frequency is determined by Einstein's relation: energy equals Planck's constant times frequency. With these 3 postulates, Bohr could calculate the frequencies of every spectral line of hydrogen. He derived Balmer's empirical formula from first principles and explained the physical reason integers appeared in it. He also predicted the existence of series of spectral lines in the ultraviolet and infrared that had not yet been observed, and they were subsequently found exactly where he said they would be. The model was a triumph. It was also, as Bohr himself understood, deeply unsatisfying. Why were only certain orbits allowed? Bohr had imposed the quantization condition as an assumption, not derived it from anything deeper. Why did electrons in these orbits not radiate? No explanation. What happened during the jump from one orbit to another? Bohr called it a quantum leap and offered no description of the process whatsoever. The electron was in one orbit, then it was in another. There was no continuous transition, no trajectory, no in-between state. It is worth pausing to appreciate how strange this is. In everyday life, things move continuously from one place to another. You cannot get from one side of a room to the other without passing through all the space in between. But Bohr's electron did not do this. It disappeared from one orbit and reappeared in another with no intervening journey. This was, at the time, an outrageous claim, but the math fit the data, so physicists were forced to take it seriously. What Bohr's model needed, and did not yet have, was a deeper reason. A reason why only certain orbits were selected. A reason why electrons behaved like they did. That reason came from the idea that electrons were not particles. They were waves. In 1924, a French doctoral student named Louis de Broglie submitted a thesis that his thesis committee was not sure what to do with. The proposal was simple to state and radical in its implications. If light, which everyone knew was a wave, could also behave like a particle. Then maybe electrons, which everyone knew were particles, could also behave like waves. De Broglie proposed that every particle with momentum has an associated wavelength. In words, the wavelength equals Planck's constant divided by the momentum of the particle. Momentum is mass multiplied by velocity. So a very massive or very fast particle has a very small wavelength, while a very light or very slow particle has a larger wavelength relative to its momentum. For an electron, the de Broglie wavelength turns out to be roughly on the scale of atomic dimensions. This is not a coincidence. This is exactly why atoms have the structure they do. If electrons are waves wrapped around the nucleus, then the only stable orbits are those in which the wave fits perfectly around the circumference of the orbit without destructively interfering with itself. In other words, the orbit must contain a whole number of wavelengths. One wavelength, two wavelengths, three wavelengths, and so on. This is exactly Bohr's quantization condition, but now it has a physical meaning. The allowed orbits are the ones where the electron wave is a standing wave, a continuous self-reinforcing wave pattern. All other orbits would have waves that interfere with themselves destructively and cancel out. De Broglie's hypothesis gave Bohr's model a physical foundation, but it raised a more fundamental question. If electrons are waves, what exactly is waving? De Broglie himself was not sure. He thought perhaps the electron was somehow accompanied by a physical wave in the ether. He was wrong about that. But the wave was real, and the experiment that proves it beyond any possible doubt is the double-slit experiment. The double-slit experiment is, by wide consensus among physicists, the most important experiment in the history of quantum mechanics. Richard Feynman called it a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery of quantum mechanics. Let us describe it carefully. You have a source of particles, let us say electrons. In front of the source, you have a barrier with two narrow slits cut into it. Behind the barrier, you have a detection screen that registers wherever an electron hits. First, you cover one slit and observe where the electrons land. They pile up in a single band directly behind the open slit. This is exactly what you expect from particles. Bullets fired through a single hole pile up in a region behind that hole. Then you cover the other slit and repeat. Again, a single band behind that slit. Again, exactly as expected. Now you open both slits and fire the electrons. If electrons are particles, the result should be simple. The electrons go through one slit or the other. The pattern on the screen should be the sum of the two single-slit patterns. Two bands, one behind each slit. But that is not what happens. What appears on the screen, after you have fired many electrons, is an interference pattern. A series of alternating bright and dark bands. Bright where the waves from the two slits arrive in phase with each other and reinforce. Dark where they arrive out of phase and cancel. This is unambiguous wave behavior. Only waves interfere this way. Two streams of particles do not cancel each other out. Two beams of bullets fired through two holes do not produce a striped pattern on a wall. The electrons must be acting as waves, passing through both slits simultaneously, interfering with each other and producing a wave-like pattern. And here is where things get really disturbing. You can turn down the source until you're firing exactly one electron at a time. 1 electron per second. Each electron arrives at the screen individually, producing a single dot. At first, the dots appear randomly scattered across the screen. But if you wait long enough, if you fire enough electrons one at a time, the dots gradually build up into an interference pattern. This means each individual electron, by itself, alone, with nothing else to interfere with, is somehow going through both slits simultaneously and interfering with itself. This is not possible for a particle. A particle is a localized thing that is either here or there. It cannot be in two places at once. It cannot go through two slits at the same time. And yet the interference pattern appears. The electron is not a particle in the classical sense. It is something for which we do not have a good word. Something that behaves like a wave when you're not measuring it, producing interference patterns that reflect its wave nature. But something that arrives at the screen at a single definite location, behaving like a particle when detected. Now the experiment gets stranger still. Suppose you decide to cheat. Suppose you place a detector next to the slits to figure out which one the electron actually went through. After all, if you know which slit the electron went through, you know which path it took, and that should tell you something about its trajectory. You set up the detector, you fire the electrons, you successfully measure which slit each electron goes through, and you look at the screen. The interference pattern is gone, completely, without trace. The electrons now pile up in two bands, one behind each slit, exactly as if they were classical particles. The act of measuring which slit the electron went through has destroyed the wave behavior. The electron now behaves like a particle. Not because the detector physically disturbed it in some way that classical mechanics could account for. Not because we accidentally pushed the electron onto a different path, but simply because the information about which path it took was acquired by the universe. The very fact that a measurement was made, the very fact that which slit information exists anywhere in the universe, collapses the electron's wave nature. This result has been tested over and over again in many different experimental configurations, with electrons, with atoms, with molecules, and even with objects large enough to be visible under an electron microscope. The result is always the same. Observation destroys interference. Physicists have even done experiments where the measurement is made after the particle has already passed through the slits, but before it hits the screen, in what are called delayed choice experiments. And still the interference pattern disappears. The electron's past behavior seems to change based on what we measure in the future. The timeline of causality in quantum mechanics does not work the way intuition expects. What does all this mean? That is the question that physicists have been arguing about for a century. But before we get to the interpretation question, we need to understand what actually governs the behavior of quantum systems. And to do that, we need to talk about Heisenberg. Werner Heisenberg was 23 years old when he developed the first complete mathematical formulation of quantum mechanics. It was 1925. He was working on the island of Helgoland, having travelled there to escape a severe hay fever attack. And in the middle of the night he made a mathematical breakthrough that, by his own account, frightened him. The mathematics he developed was strange. It involved quantities that, when multiplied, did not commute. In ordinary arithmetic, 3 times 4 equals 4 times 3. But in Heisenberg's formulation of quantum mechanics, the mathematical objects representing physical quantities like position and momentum did not satisfy this rule. The product of the position operator times the momentum operator was not the same as the product of the momentum operator times the position operator. They differed by a specific amount. The imaginary unit times Planck's constant divided by 2pi. This non-commutativity had a profound physical consequence. Heisenberg worked it out, and in 1927 he published his famous uncertainty principle. The uncertainty principle states in the most precise form that the uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to Planck's constant divided by 4pi. What this means in plain language is the following. The more precisely you know where a particle is, the less precisely you can know how fast it is moving and in what direction. And the more precisely you know how fast it is moving, the less precisely you can know where it is. This is not a statement about limitations of measurement technology. This is not saying that our instruments are not good enough. This is not saying that measuring something disturbs it in a classical way, the way prodding a sleeping cat wakes it up. This is a statement about the nature of reality itself. Position and momentum do not both have simultaneously precise values. The universe simply does not assign them. If you pin down the position precisely, the momentum becomes genuinely undefined, not unknown, but undefined. It does not have a precise value. The particle does not have a definite momentum in that moment. This is a completely alien concept to classical intuition. In Newtonian mechanics, every particle has a definite position and a definite momentum at every moment in time. That is what it means to be a particle. In quantum mechanics, this is simply not true. There are other pairs of quantities that share this relationship. Energy and time form another such pair. The uncertainty in energy multiplied by the uncertainty in time is also greater than or equal to Planck's constant divided by 4pi. This means that a quantum state with a precisely defined energy must exist for an infinite time. Conversely, a quantum state that exists for only a very short time has a fundamentally uncertain energy. This energy-time uncertainty has real, measurable consequences. One consequence is the natural line width of spectral lines. When an atom emits a photon and returns to its ground state, the emitted light is not at a perfectly sharp frequency. It has a small spread of frequencies because the excited state lasts for only a finite time before decaying. The shorter the lifetime of the excited state, the broader the spread in frequency of the emitted light. This is directly measurable, and it exactly matches the prediction of the uncertainty principle. Another profound consequence of energy-time uncertainty is the stability of the ground state. Consider a hydrogen atom in its lowest energy state. The electron is as close to the nucleus as it can get while still satisfying the uncertainty principle. Why does it not fall all the way into the nucleus? Because if you confined the electron to a smaller and smaller region, its position uncertainty would decrease, which means its momentum uncertainty would increase, which means it would have more kinetic energy. At some point, the kinetic energy gained by further confinement exceeds the potential energy gained by moving closer to the nucleus, and the electron cannot go further in. The uncertainty principle is what prevents electrons from collapsing into atomic nuclei. It is literally what makes atoms stable. It is what makes matter possible. Without Heisenberg's uncertainty principle, every atom in the universe would immediately collapse. You would not exist. Nothing would exist. The uncertainty principle also has a consequence that sounds like science fiction, but is completely real. Because of energy-time uncertainty, even completely empty space is not really empty. In any region of space, pairs of particles and antiparticles spontaneously appear, exist for a tiny fraction of a second, and then annihilate each other. These are called virtual particles, and they are a real, measurable phenomenon. The Casimir effect, an attraction between two uncharged metal plates placed very close together in a vacuum, is caused by virtual particles and has been measured precisely in the laboratory. Empty space is seething with quantum activity. The vacuum is not empty. And all of this follows from Heisenberg's uncertainty principle. But Heisenberg's work left open a fundamental question. If particles do not have definite positions and momenta, what exactly is it that quantum mechanics describes? What is the mathematical object that represents the state of a quantum system? The answer to that question came from Erwin Schrödinger in 1926. Erwin Schrödinger was, by the standards of 1926, a middle-aged physicist who had done solid but not spectacular work. He was 38 years old, which in theoretical physics was considered somewhat past the prime age for revolutionary discoveries. He was attending a Christmas seminar in late 1925, at which a young colleague presented de Broglie's idea of matter waves, and someone remarked that if electrons were waves, there ought to be a wave equation governing their behavior. Schrödinger took this remark seriously. Over the following weeks, working with extraordinary intensity, he derived what is now called the Schrödinger equation. It is, by many measures, the most important equation in all of chemistry and one of the most important in all of physics. The Schrödinger equation describes how the quantum state of a physical system evolves over time. But the quantum state in Schrödinger's formulation is not a description of where a particle is or how fast it is moving in a classical sense. It is a wave function, typically denoted by the Greek letter psi. The wave function is a mathematical object that, in its simplest form, assigns a complex number, a number that has both a real part and an imaginary part, to every point in space. What does this complex wave function mean physically? That question consumed physicists for years. The answer, proposed by Max Born in 1926 and now universally accepted, is that the wave function is a probability amplitude. More specifically, the square of the absolute value of the wave function at any point in space gives the probability density of finding the particle at that point if you make a measurement. In words, if you measure the position of a particle, you will find it at a particular location, but which location you find it at is not predetermined. It is governed by probability. The wave function tells you the probability distribution, how likely you are to find the particle in any given region. But before you make the measurement, the particle does not have a definite position. The wave function is not describing your ignorance of a position the particle secretly has. The particle genuinely does not have a definite position. It exists in a superposition of all possible positions, each weighted by the corresponding probability amplitude. This interpretation, that the wave function represents genuine probability, not just ignorance, was deeply disturbing to many physicists, including Schrödinger himself. Einstein famously objected that God does not play dice with the universe, meaning he could not accept that nature was fundamentally probabilistic. He believed the probabilities in quantum mechanics reflected our ignorance of some deeper layer of deterministic physics, what he called hidden variables. He was wrong. We will explain exactly how we know that when we get to entanglement. Schrödinger's equation has a remarkable property. It is completely deterministic. Given the wave function of a system at any moment, the Schrödinger equation tells you exactly what the wave function will be at any future moment. There is nothing random about the evolution of the wave function. It evolves smoothly, continuously, and deterministically, like any classical wave. The randomness enters only at measurement. When you make a measurement, the wave function, which had been spread out over many possible values, suddenly and discontinuously collapses to a single value. This is called wave function collapse, and it is the most controversial step in all of quantum mechanics. No one knows what causes wave function collapse. No one knows exactly when it happens. No one knows whether it is a real physical process or a mathematical bookkeeping procedure. The Schrödinger equation itself says nothing about collapse. If you apply the Schrödinger equation to everything, including the measuring apparatus, the observer, and the universe as a whole, you never get collapse. You just get a larger and larger superposition. This is the measurement problem, and it is the deepest unsolved problem in the foundations of quantum mechanics. To illustrate how bizarre this situation is, Schrödinger proposed one of the most famous thought experiments in the history of science, Schrödinger's cat. Imagine a sealed box containing a cat. Inside the box there is also a small amount of radioactive material, a Geiger counter connected to a relay mechanism, and a vial of poison gas. The setup is arranged so that if the Geiger counter detects a decay event from the radioactive material, it triggers the relay, which shatters the vial and releases the poison, killing the cat. The amount of radioactive material is chosen so that after 1 hour there is exactly a 50% probability that one decay event has occurred. Now you close the box and wait an hour. According to quantum mechanics, the radioactive atom exists in a superposition of decayed and not decayed states, each with equal probability. The Geiger counter is entangled with the atom. It is in a superposition of having triggered and not having triggered. The relay is in a superposition. The poison vial is in a superposition of broken and intact. And therefore the cat is in a superposition of alive and dead. Not alive with some hidden unknown status. Genuinely, according to the Schrödinger equation, in a superposition of both states simultaneously. When you open the box and look, the wave function collapses and you see one definite outcome, a live cat or a dead cat. But before you look, is the cat alive or dead? Schrödinger proposed this thought experiment not to suggest that cats could be in superposition, but to demonstrate what he considered the absurdity of applying quantum mechanics to macroscopic objects. He thought the theory was incomplete. He thought there had to be some additional physics that prevented macroscopic superpositions from forming. He was right that something additional is needed to explain why we never observe cats in superpositions. But what that something is remains one of the deepest questions in physics. Different interpretations of quantum mechanics answer this question in radically different ways, and we're going to go through them. But first, we need to understand the dominant interpretation, the one that most working physicists use most of the time, even if they have reservations about it. In the late 1920s, Niels Bohr and Werner Heisenberg developed an interpretation of quantum mechanics that came to be called the Copenhagen interpretation, named after the city where Bohr's institute was located. It became the standard interpretation, taught in textbooks, used by working physicists, and accepted as the default view for most of the 20th century. Understanding it is essential, not because it is definitely correct, but because it is the foundation against which all other interpretations are measured. The Copenhagen interpretation has several key components. First, the wave function is a complete description of a quantum system. There's no deeper reality hidden behind it, no hidden variables, no secret deterministic machinery underneath the probabilities. The wave function is everything there is to know about the system. Second, physical quantities do not have definite values until they are measured. Before measurement, a particle does not have a definite position or momentum or spin. It exists in a superposition of possible values. The act of measurement forces the system to choose a value according to the probability distribution encoded in the wave function. Third, measurement causes wave function collapse. After a measurement yields a particular value, the wave function is now that value, not the original superposition. Subsequent measurements will give the same result consistently. Fourth, there is a fundamental divide between the quantum world and the classical world. Quantum systems, atoms, electrons, photons, obey quantum mechanics. Classical systems, measuring apparatus, observers, macroscopic objects, obey classical physics. Quantum mechanics applies to the quantum system being measured, but the measuring apparatus is described classically. Fifth, and most provocatively, it is meaningless to ask what the system was doing before measurement. There is no fact of the matter about the position of an electron before you measure it. Asking where the electron was when you were not looking is, in Copenhagen, a category error. Like asking what is north of the North Pole. The question has no answer because it is not a well-formed question. Bohr summarized this attitude with his concept of complementarity. Some properties of a quantum system are complementary, meaning they cannot be simultaneously defined with precision. Wave behavior and particle behavior are complementary. Position and momentum are complementary. When you observe one, you necessarily forego information about the other. Neither is more real than the other. They are both aspects of a single quantum reality that cannot be captured in a single classical picture. The Copenhagen interpretation is pragmatically very powerful. It tells you exactly how to calculate the outcomes of experiments, and it matches the data perfectly. Every prediction ever made using the Copenhagen interpretation has been confirmed by experiment. But it leaves several questions unanswered. What exactly is a measurement? Where exactly is the boundary between quantum and classical? What actually happens during wave function collapse? Is it a real physical process or just a mathematical update? What is the ontological status of the wave function? Does it represent reality or just our knowledge? Bohr's answer to most of these questions was essentially, stop asking. Physics is about predicting the outcomes of experiments. If you can predict all outcomes correctly, that is all physics needs to do. The question of what is real underlying the formalism is metaphysics, not physics. This attitude, often summarized as shut up and calculate, was enormously influential. It let physicists get on with the business of applying quantum mechanics to atomic physics, nuclear physics, solid-state physics and chemistry without getting bogged down in philosophical questions. And the applications were spectacularly successful. But for many physicists, the shut-up and calculate approach was never satisfying. It felt like ignoring the deepest question the theory raised. And the deepest question was this: if the wave function does not collapse for quantum systems until measurement, and if measuring apparatus and observers are themselves made of atoms that obey quantum mechanics, then why does anything ever collapse at all? That question led John von Neumann in 1932 to the uncomfortable conclusion that wave function collapse might require a conscious observer. That idea was taken seriously by some physicists and is still discussed today, though most physicists reject it. But the question remains unanswered, and the attempts to answer it have led to some of the most extraordinary ideas in the history of science. Superposition is the central feature that makes quantum mechanics different from everything else. It is not just a strange fact about particles. It is a mathematical principle built into the structure of the theory, and it has consequences that extend far beyond the double-slit experiment. In quantum mechanics, the state of a system is represented by a vector in a mathematical space called a Hilbert space. The rules of this space allow any two valid state vectors to be added together with complex number coefficients to produce another valid state vector. This is superposition. If a quantum system can be in state A and it can be in state B, then it can also be in a superposition, some amount of A plus some amount of B. The coefficients of the superposition are the probability amplitudes. Their squares give the probabilities of finding the system in one state or the other when you make a measurement. But while no measurement is being made, the system is genuinely in both states simultaneously, not flickering between them, not secretly in one of them with us just not knowing which. Both, simultaneously, at the same time. This applies to every measurable property a quantum system can have. An electron's spin, a quantum mechanical property that loosely resembles angular momentum, can be either up or down along any chosen axis. But it can also be in a superposition of up and down. A photon's polarization can be horizontal or vertical, or any superposition of the two. An atom can be in its ground state or its excited state, or any superposition of the two. And crucially, superpositions can span vastly different physical configurations. The Schrödinger's cat state is a superposition of cat alive, an atom not decayed, and cat dead, an atom decayed. A molecule can be in a superposition of having reacted and not having reacted. There is no obvious limit within the Schrödinger equation itself to the scale of superpositions that can form. So why do we never see macroscopic superpositions? Why is a cat never actually in a superposition of alive and dead in a way we could observe? The answer, worked out in detail over the last few decades, involves a process called decoherence. Any real physical system is not isolated. It constantly interacts with its environment, with air molecules, with photons, with electromagnetic fields. When a quantum system in a superposition interacts with its environment, the superposition does not disappear. Instead, the quantum system becomes entangled with a vast number of environmental degrees of freedom. The superposition spreads out into the environment. The information about which part of the superposition the system is in becomes distributed among trillions and trillions of environmental degrees of freedom. For all practical purposes, this makes the superposition unobservable. To detect the interference between the two parts of the superposition, you would need to access all the environmental information and reverse the entanglement. A task that is not merely difficult, but effectively impossible for macroscopic objects. The different parts of the superposition no longer interfere with each other. They behave as if they were separate, classical alternatives. This process of decoherence happens extremely rapidly for macroscopic objects. For a cat-sized object in normal air, decoherence would occur on timescales of roughly 10 to the power of negative 30 seconds. That is 1,000,000 times faster than the fastest processes we can currently measure. Which is why we never actually see a cat in superposition. By the time we could possibly observe interference effects, they are already gone, washed away into the environment. Decoherence explains why the classical world emerges from the quantum world for large objects, but it does not fully solve the measurement problem. Decoherence tells you why you cannot observe interference between macroscopic superpositions. It does not tell you why, when you make a measurement, you get one specific outcome rather than remaining in a superposition. Decoherence turns a quantum superposition into something that looks like a classical probability distribution. 50% alive, 50% dead, but it does not explain why you open the box and see a live cat rather than experiencing both outcomes simultaneously. That remaining puzzle is exactly what the different interpretations of quantum mechanics are wrestling with. Now we come to what is arguably the most astonishing, most experimentally verified, and most philosophically disturbing phenomenon in all of quantum mechanics: quantum entanglement. When two particles interact in certain ways, they can form a joint quantum state that cannot be written as a product of two independent states for the two particles. The two particles are said to be entangled. Their quantum states are correlated in a way that has no classical analogue. Here is the simplest example. Take two electrons and prepare them in a state called the singlet state. In this state, the total spin of the two electrons is 0. One electron is spin up and the other is spin down. But quantum mechanics does not specify which is which. The state is a superposition. Electron 1 up and electron 2 down, plus electron 1 down and electron 2 up, with equal amplitudes. Now separate the two electrons. Send one to a laboratory in New York and one to a laboratory in Tokyo. Now measure the spin of the electron in New York along any axis, say the vertical axis. You will get either up or down, each with 50% probability. Suppose you get up. Then, according to quantum mechanics, the electron in Tokyo is now definitely spin down along that same axis. And if you had gotten down in New York, Tokyo would be up. The two measurements are perfectly anti-correlated. This alone is not yet strange. You might think the two electrons simply had their spin values set at the moment they were prepared, like a pair of gloves. One left-handed and one right-handed. Separate them, look at one, and instantly know what the other one is. No mystery there. But quantum mechanics says something stronger. It says the electrons do not have definite spin values before measurement. They are genuinely in superposition until one of them is measured. And here is how we can test whether that claim is true. In 1964, the physicist John Bell derived a remarkable mathematical result. He showed that if quantum mechanics was correct about superposition, if the correlations between entangled particles were genuinely quantum rather than the result of pre-assigned hidden values, and then experiments measuring correlations at different angles would yield results that violated a certain mathematical inequality. This is called Bell's inequality. In words, if hidden variables were responsible for the correlations, if the particles carried predetermined values that determined the measurement outcomes, then the correlation between measurements along different axes could not exceed a certain bound. But quantum mechanics predicts correlations that exceed that bound. Beginning in the 1970s, physicists began performing experiments to test Bell's inequality. Alain Aspect and his collaborators in Paris performed a landmark series of tests in 1982. Their results violated Bell's inequality in quantitative agreement with the predictions of quantum mechanics. Every subsequent test, and there have been many, closing various theoretical loopholes one by one, has confirmed the violation. In 2015, a group of physicists performed what is called a loophole-free Bell test, simultaneously closing all the major theoretical loopholes. The result was a clear violation of Bell's inequality. The conclusion is unavoidable. The correlations between entangled particles are not the result of hidden predetermined values. Quantum mechanics is correct. Before measurement, the particles genuinely do not have definite values. The correlations are real, and they cannot be explained by any theory that assigns local hidden variables to the particles before measurement. Einstein called this spooky action at a distance, meaning that measuring one particle seems to instantaneously affect the other, regardless of the distance between them. He found this deeply objectionable and spent decades trying to find a way around it. But Einstein was wrong. Spooky action at a distance is real. Not in the sense that information travels faster than light. It does not. You cannot use entanglement to send signals, because the outcomes of individual measurements are random, and there is no way to control what result you get. But the correlations are real, and they cannot be accounted for without abandoning either locality, the idea that distant events cannot directly affect each other, or realism. The idea that physical properties have definite values independent of observation. You can give up locality, or you can give up realism. But according to Bell's theorem, you cannot keep both. Most physicists choose to give up local realism, the combination of locality and realism that Einstein held dear. The universe is either non-local, meaning distant events can be correlated in ways that transcend classical notions of space, or it is not real in the sense of having definite properties independent of observation, or both. This is not a matter of interpretation or philosophy. It is a mathematical theorem confirmed by experiment. Entanglement is not just a theoretical curiosity. It is a real physical resource, and it is being harnessed right now in quantum technologies. Quantum cryptography uses entanglement to create communication channels that are provably secure against any eavesdropping. Quantum teleportation, the transfer of quantum states from one location to another without physically moving the particle, uses entanglement as its resource. Quantum computing, which we will discuss in detail later, relies fundamentally on entanglement to achieve its power. But before we get to quantum computing, we need to talk about one more phenomenon that illustrates the strangeness of quantum mechanics in a different way. A phenomenon that should be completely impossible, and yet makes the sun shine. In classical physics, a ball sitting in a valley cannot escape over a surrounding hill unless it has enough energy to climb that hill. This is just energy conservation. You cannot get something for nothing. If the hill is higher than the ball's total energy, the ball cannot get over. Period. End of story. In quantum mechanics, the story is different. Because quantum particles are described by wave functions, not classical trajectories, and wave functions do not just stop at classical forbidden boundaries. They decay exponentially inside barriers, but they do not become zero immediately. If the barrier is thin enough, the wave function has a small but non-zero value on the other side of the barrier. And a non-zero wave function means a non-zero probability. A quantum particle can be found on the far side of a barrier it classically could not cross. It has tunneled through the barrier, not over it, through it. This is not a metaphor. This is literally what happens. The particle passes through a region of space that is energetically forbidden to it by the rules of classical physics. It does not go over the barrier, around the barrier, or through a gap in the barrier. The barrier is solid and unbroken, and the particle goes through it anyway. How is this possible? Because the particle's position is described by a probability wave, not a classical trajectory. The uncertainty principle means the particle cannot have both a definite position and a definite momentum simultaneously. This uncertainty allows the particle to briefly violate energy conservation in ways that are unmeasurable by any conceivable experiment, but that have a cumulative effect. A small but non-zero probability of appearing on the far side of the barrier. Tunneling is not a rare theoretical curiosity. It is one of the most important phenomena in nature. The Sun fuses hydrogen nuclei into helium in its core. For two hydrogen nuclei to fuse, they must come close enough together that the strong nuclear force can grab them and bind them. But both nuclei are positively charged and, like charges, repel. The electrostatic repulsion between two protons is an energy barrier. For two protons to come close enough to fuse, they would need, by classical calculation, to have much more energy than they actually have at the temperature of the Sun's core. The temperature at the center of the Sun is about 15 million Kelvin. At that temperature, most protons simply do not have enough energy to overcome the Coulomb barrier by any classical means. But they do not need to. They tunnel through it. The probability of tunneling for any single pair of protons is unimaginably small, but there are roughly 10 to the power of 57 protons in the Sun. At any given moment, many billions of pairs are tunneling successfully and fusing. The Sun's energy output is powered by quantum tunneling. Every photon of sunlight that has ever reached Earth got its start in the quantum mechanical tunneling of two protons in the Sun's core. Life on Earth exists because of quantum tunneling. Tunneling also operates inside your body at the biochemical level. Enzyme catalysis, the process by which biological enzymes speed up chemical reactions, involves proton tunneling. Some enzymes achieve their remarkable catalytic efficiency partly by providing an environment in which protons can tunnel efficiently from one chemical group to another. DNA mutation, which is both essential for evolution and the source of some cancer mutations, involves proton tunneling within the hydrogen bonds of the DNA double helix. Tunneling is also the basis of the scanning tunneling microscope, a device invented in 1981 that can image individual atoms on a surface. In a scanning tunneling microscope, a conducting tip is brought to within a few atomic diameters of a conducting surface. Even though the tip and the surface do not touch, electrons tunnel across the vacuum gap between them. The current that flows is exquisitely sensitive to the distance of the gap, varying by roughly a factor of 10 for every angstrom, every 1/10 of a nanometer, of change in gap distance. By scanning the tip across the surface and measuring the tunneling current, you can map the surface with atomic scale resolution. Tunneling is also the operating principle of the flash memory in every smartphone and solid-state drive. Data is stored and erased by moving electrons through thin insulating barriers via quantum tunneling. Every time you save a file, quantum mechanics saves it. Now we need to address the interpretational elephant in the room. We have talked about the Copenhagen interpretation, we have talked about decoherence, we have talked about wave function collapse, but we have not yet asked what actually happens to the cat when we open the box. What actually happens during a measurement? The most radical answer to this question came not from Bohr or Heisenberg, but from a young American physicist who proposed something that sounded, when first published, completely insane. In 1957, Hugh Everett III, a graduate student at Princeton University, submitted his doctoral thesis proposing what is now called the many worlds interpretation of quantum mechanics. The core idea is simple to state. The Schrödinger equation always holds, always, without exception. Wave function collapse never happens. When you open Schrödinger's box and look at the cat, you do not cause the wave function to collapse. Instead, you become entangled with the cat. Your own quantum state enters a superposition. The version of you that sees a live cat and the version of you that sees a dead cat. Both versions of you exist. Both are real. Both go on to have their own subsequent experiences. The universe itself, on this view, is in a gigantic superposition of all possible histories. Every quantum measurement that has ever occurred has branched the universe into multiple versions. Each branch is equally real. Each contains observers who experience a single definite outcome, consistent with quantum mechanical probabilities. The reason any particular version of you sees a definite outcome when you make a measurement is not because the wave function collapsed. It is because within your branch, one outcome occurred, and the other outcomes are in branches that have decohered and cannot interfere with yours. The many worlds interpretation solves the measurement problem by eliminating collapse entirely. The Schrödinger equation is complete and universal. There is no need for a separate rule for measurement. Measurement is just a physical interaction like any other, and it always produces entanglement, not collapse. This interpretation has real advantages. It is mathematically consistent. It requires no additional axioms beyond the Schrödinger equation and Born's rule for calculating probabilities. It removes the mysterious divide between the quantum world and the classical world. Everything is quantum. Classical physics emerges from quantum mechanics through decoherence. It also has serious challenges. The most pressing is the question of probability. If all branches are real, and observers in all branches have equally real experiences, then what does it mean to say that a measurement outcome has a certain probability? Why should you care that one outcome has a higher probability than another if both outcomes happen in different branches with certainty? Deriving Born's rule, the rule that says probability is proportional to the square of the wave function amplitude, within the many worlds framework is a major unsolved problem, though various attempts have been made. There is also the question of what exactly constitutes a branch. The Schrödinger equation does not divide the universe into branches. The branching emerges through decoherence, but decoherence does not define branches uniquely. Different ways of dividing up the universal wave function give different numbers of branches. Some physicists consider this a fatal flaw. Others consider it a matter of definition rather than physics. And there is the sheer conceptual cost of the interpretation. The many worlds interpretation says that every quantum event, every radioactive decay, every measurement, every interaction branches the universe into multiple copies. The number of branches grows at a rate that is effectively beyond comprehension. Every second, a staggering number of new branches come into existence. Most physicists find this ontological extravagance uncomfortable, though some argue that existence is cheap and the interpretation is worth the cost. The many worlds interpretation is currently probably the most popular interpretation among physicists who think carefully about foundations, though polling results are uncertain and the field is divided. Other interpretations exist and deserve mention. The pilot wave interpretation, also called de Broglie-Bohm theory or Bohmian mechanics, was fully developed by David Bohm in 1952. It restores determinism to quantum mechanics by positing that particles always have definite positions and are guided by a real physical wave, the pilot wave, that obeys the Schrödinger equation. There is no wave function collapse and no measurement problem. Measurement outcomes are determined by the actual positions of particles, which are definite at all times. The probabilities arise from ignorance of the exact initial conditions, not from fundamental indeterminism. The pilot wave theory reproduces all the predictions of standard quantum mechanics exactly. It is empirically indistinguishable from the Copenhagen interpretation. The price of this determinism and realism is non-locality. The pilot wave of a many-particle system lives in configuration space, not in ordinary three-dimensional space, and it is inherently non-local. Changes in the wave function at one location can instantaneously affect the guidance of particles at any other location. Many physicists find this non-locality deeply uncomfortable, especially given its tension with special relativity. There is also the relational interpretation proposed by Carlo Rovelli. On this view, quantum states are relational. They describe the state of a system relative to a particular observer or measurement context. Different observers may assign different wave functions to the same system, and both descriptions can be correct within their own reference frame. The relational interpretation sidesteps the measurement problem by defining what counts as a measurement very broadly. Any physical interaction counts. and by insisting that quantum states are not absolute but relative. There is cubism, quantum Bayesianism, developed by Christopher Fuchs, Rudiger Schack, and David Mermin. On this view, the wave function is not a description of physical reality at all. It is an agent's representation of their personal beliefs about the outcomes of future measurements. Wave function collapse is not a physical event. It is simply the agent updating their beliefs upon receiving new information. Cubism eliminates the measurement problem entirely by making quantum mechanics a theory about agents' experiences and expectations, not a theory about objective reality. Critics object that this makes quantum mechanics a theory about human experience rather than physics, and that it fails to explain why the world behaves consistently for different agents. The honest situation is this. We have a mathematical formalism, the Schrödinger equation combined with Born's rule, that works perfectly. It predicts the outcomes of experiments with extraordinary precision. But we do not have agreement on what that formalism means. We do not know whether the wave function represents reality or knowledge. We do not know whether measurement involves a physical collapse or branching or simply a relational update. We do not know whether the world is fundamentally deterministic or fundamentally random. These are not merely philosophical questions. Different interpretations make different predictions in certain exotic scenarios, and future experiments may be able to distinguish between them. The interpretation question may not be forever beyond experimental reach, but for now it remains one of the deepest open problems in all of science. Everything we have discussed so far, wave functions, superposition, entanglement, uncertainty, is non-relativistic quantum mechanics. It works beautifully for atoms, molecules and electrons moving at non-relativistic speeds, but it ignores special relativity. And special relativity is real. Particles can move at speeds close to the speed of light. Particles can be created and destroyed. And any complete theory of quantum mechanics needs to be consistent with the rules of special relativity. The synthesis of quantum mechanics and special relativity is called quantum field theory. It was developed primarily in the 1930s through the 1940s by Paul Dirac, Wolfgang Pauli, Shinichiro Tomonaga, Julian Schwinger, Richard Feynman, and Freeman Dyson, among others. It is, by all measures, the most successful physical theory ever constructed. The central conceptual shift of quantum field theory is this. In quantum mechanics, particles are fundamental objects, and we describe their behavior using wave functions. In quantum field theory, fields are fundamental, and particles are excitations of those fields. Think of a field as something that permeates all of space. There is an electron field everywhere in the universe. An electron is not a fundamental object in its own right. An electron is a localized vibration, a quantum of excitation in the electron field. In the same way, a photon is a quantum of excitation of the electromagnetic field. Each species of elementary particle corresponds to a quantum field. The standard model of particle physics, our best current theory of the fundamental constituents of matter, contains fields for quarks, electrons, muons, tau particles, neutrinos, photons, gluons, W bosons, Z bosons, and the Higgs field. Each of these fields permeates all of space. Each field can be in its ground state, with no particles present, or it can be excited, with one or more particles present. Particles are not little balls. Particles are field excitations. The interaction between fields explains how particles interact. When an electron emits a photon, the electron field interacts with the electromagnetic field, creating an excitation in the electromagnetic field, a photon, while changing the state of the electron field. All forces in quantum field theory are mediated by the exchange of virtual particles, virtual excitations of force-carrying fields. The electromagnetic force is mediated by virtual photons. The strong nuclear force, which holds quarks together inside protons and neutrons, is mediated by virtual gluons. The weak nuclear force, responsible for radioactive beta decay, is mediated by virtual W and Z bosons. Quantum electrodynamics, the quantum field theory of the electromagnetic interaction, is the most precisely tested theory in all of science. It predicts the magnetic moment of the electron, a measure of how strongly the electron behaves like a tiny magnet, with a precision of better than 1 part in 1 trillion. The experimental measurement agrees with the theoretical prediction to 12 decimal places. This is like measuring the distance from New York to Los Angeles and getting the answer right to within the thickness of a human hair. Quantum field theory also predicts, and experiments confirm, processes that are completely impossible in classical physics. Pair production. A photon can convert into an electron and a positron, the antimatter partner of the electron, if it has enough energy. The positron is a particle with the same mass as the electron, but opposite electric charge. Pair annihilation. An electron and a positron can annihilate each other, producing 2 photons. Virtual particle effects. Loops of virtual particles in the vacuum contribute to measurable physical quantities, and these contributions have been calculated and verified. The Higgs mechanism, a central part of quantum field theory, explains why the W and Z bosons have mass while the photon is massless. It involves a field, the Higgs field, that permeates all of space in a non-zero configuration, called a vacuum expectation value. Particles that interact with the Higgs field acquire mass as a result of this interaction. The Higgs boson, the quantum excitation of the Higgs field, was discovered at the Large Hadron Collider at CERN in 2012. Its mass was measured to be approximately 125 giga-electron volts divided by the speed of light squared. Its discovery completed the Standard Model. Quantum field theory is not just an academic success. It has real-world applications. MRI scanners, magnetic resonance imaging machines found in hospitals everywhere, rely on the quantum mechanics of nuclear spin, which quantum field theory describes. Positron emission tomography, PET scanning, uses the annihilation of positrons with electrons to image biological processes inside living bodies. Lasers, transistors, LEDs, solar cells all depend on quantum mechanical effects that quantum field theory either directly predicts or underpins. But quantum field theory has its own deep problem. It does not include gravity. General relativity, Einstein's theory of gravity, describes space-time itself as a dynamical entity that curves in response to matter and energy. When physicists attempt to quantize gravity, to build a quantum field theory of the gravitational field, the mathematics produces infinite, uncontrollable divergences. The calculations give nonsensical infinite answers for physically finite quantities. This problem has resisted solution for nearly a century. String theory is one attempt to solve it. Loop quantum gravity is another. Neither has yet made predictions that experiment can test. The reconciliation of quantum mechanics and general relativity is the deepest unsolved problem in theoretical physics, and it is not even close to being solved. But the quantum world is not waiting for us to solve its deepest problems. Right now, engineers and physicists are building machines that exploit quantum mechanical principles in ways that will change computation, communication, and sensing more profoundly than the transistor changed them. A classical computer stores and processes information using bits. Each bit is either 0 or 1. A transistor is either on or off. A memory cell is either magnetized or not. The entire computational edifice of the modern world, every calculation ever performed by every computer, smartphone, server, or embedded processor, rests on the manipulation of strings of zeros and ones according to logical rules. A quantum computer stores and processes information using quantum bits called qubits. A qubit is a quantum system that can be in the state 0 or the state 1 or any quantum superposition of 0 and 1. This distinction seems subtle. It is not. A single qubit can be in a superposition of 0 and 1 simultaneously. 2 qubits can be in a superposition of all 4 2-bit strings, 0, 0, 0, 1, 1, 0, and 1, 1, simultaneously. 3 qubits can be in a superposition of all 8 3-bit strings simultaneously. In general, n qubits can be in a superposition of all 2 to the power of n states simultaneously. For 300 qubits, this means a superposition of 2 to the power of 300 states. 2 to the power of 300 is a number larger than the estimated number of atoms in the observable universe. A 300-qubit quantum computer can, in some sense, be in more states simultaneously than there are atoms in the universe. But here is the critical point that prevents quantum computers from just being infinitely powerful parallel classical computers. You cannot read out all those states simultaneously. When you measure a quantum system, you get a single classical result, chosen according to the probability distribution encoded in the quantum state. You do not get all the answers at once. You get one answer. The art of quantum algorithm design is figuring out how to use quantum interference, the wave-like nature of superpositions, to amplify the probability of correct answers and suppress the probability of wrong answers, so that when you measure, you are very likely to get a useful result. This is extraordinarily difficult to do. Most questions cannot be answered more efficiently with a quantum computer than with a classical one. Quantum computers are not universally faster. They are specifically faster for specific types of problems that have special mathematical structure that quantum algorithms can exploit. But for those problems, the speed-up can be exponential. Peter Shor's algorithm, published in 1994, shows that a quantum computer can factor large integers exponentially faster than any known classical algorithm. This matters enormously for cryptography. The security of RSA encryption, the encryption system used to protect most internet traffic, banking transactions, and secure communications, is based on the difficulty of factoring large numbers. Multiplying two large prime numbers together is easy. Given their product, finding the two original primes is believed to be computationally intractable for a classical computer when the numbers are large enough. A number that is the product of 2,000-digit primes would take a classical computer longer than the age of the universe to factor using the best-known algorithms. A sufficiently powerful quantum computer running Shor's algorithm could factor that number in hours or days. This is why the development of quantum computers is a matter of serious national security concern for every government with a major digital infrastructure. And why the development of post-quantum cryptography, encryption algorithms that cannot be broken by quantum computers, is an active area of research right now. The United States National Institute of Standards and Technology has been running a competition to standardize post-quantum cryptographic algorithms, and the first standards were published in 2024. The other landmark quantum algorithm is Grover's algorithm, published in 1996. Grover's algorithm solves the problem of searching an unsorted list of n items for a specific item in a number of steps proportional to the square root of n. A classical computer needs, in the worst case, n steps for the same task, because it might need to check every item. A quantum computer using Grover's algorithm needs only the square root of n steps. For a list of 1 million items, that is the difference between 1 million steps and 1,000 steps. For 1 trillion items, the difference is 1 trillion versus 1 million. Beyond factoring and search, quantum computers are expected to be useful for simulating quantum systems, which is computationally intractable for classical computers because quantum systems involve exponentially large amounts of information. For optimization problems, for machine learning, and for solving certain systems of linear equations. Where are we with actual quantum computers? The field has advanced dramatically in the last decade. In 2019, Google announced that their 53-qubit processor called Sycamore had performed a specific calculation in about 200 seconds that they estimated would take the fastest classical supercomputer approximately 10,000 years. IBM disputed those timescales, but the demonstration was a milestone. IBM, Google, IonQ, Quantinuum, and several other companies are all pursuing quantum computing with different physical implementations. Qubits can be realized in superconducting circuits, in trapped ions, in photons, in neutral atoms, in semiconductor quantum dots, and in nitrogen vacancy centers in diamond. Each approach has different strengths, different error rates, and different scalability prospects. The central challenge in all current quantum computing hardware is decoherence and error. Qubits are exquisitely sensitive to environmental disturbances. Any interaction with the environment causes decoherence, destroying the quantum superposition and introducing errors. Current quantum computers are what researchers call noisy intermediate-scale quantum, or NISQ, devices. They have tens to hundreds of qubits, but those qubits are not perfect, and errors accumulate rapidly as computations grow longer. To perform the large-scale computations that would be needed to break RSA encryption or simulate complex chemical reactions accurately, quantum computers need to implement quantum error correction. Quantum error correction encodes one logical qubit in many physical qubits and uses redundancy to detect and correct errors. The overhead is substantial. Estimates suggest that a fully fault-tolerant quantum computer capable of running Shor's algorithm to threaten current encryption standards might require thousands of physical qubits per logical qubit. A practical implementation might need millions or tens of millions of physical qubits. Current systems have hundreds to thousands of physical qubits. The gap is large, but it is narrowing. In 2023, Google demonstrated a clear improvement in logical qubit error rates as they increased the number of physical qubits per logical qubit, showing that their error correction approach was working. This was a significant milestone, demonstrating that the theory of quantum error correction works in practice and that scaling up should improve rather than degrade performance. Many experts believe that practical, fault-tolerant quantum computers are not decades away. Some believe we may have them within 10 to 15 years. Others are more cautious. The engineering challenges are enormous, but the progress has been faster than many predicted even 5 years ago. Quantum computing is not the only quantum technology being actively developed. Quantum sensing is already delivering practical devices. Quantum sensors exploit quantum mechanical precision. Specifically, the exquisite sensitivity of quantum systems to external perturbations, to make measurements of extraordinary accuracy. Atomic clocks based on quantum transitions are currently so precise that they would neither gain nor lose more than 1 second in 300 million years. These clocks are the basis of GPS navigation. The timing signals from GPS satellites relayed to your phone allow your location to be determined to within a few meters. That precision is entirely dependent on quantum mechanical timekeeping. Quantum magnetometers are sensitive enough to detect the tiny magnetic fields produced by the electrical currents in the human brain. This opens the possibility of non-invasive brain scanning, with spatial and temporal resolution far beyond what current technologies achieve. Quantum gravimeters can detect tiny variations in the gravitational field and are being used for geological surveys, for oil and mineral exploration, and for monitoring volcanic activity. Quantum communication networks are being built in multiple countries. China has deployed a quantum communication satellite and a fiber-optic quantum network connecting Beijing and Shanghai. The European Quantum Flagship Program is funding large-scale quantum network development. These networks use quantum key distribution, QKD, to generate and distribute encryption keys in a way that is provably secure against any eavesdropper, because eavesdropping on a quantum communication channel necessarily disturbs it in a detectable way due to the no-cloning theorem. The no-cloning theorem, proven in 1982, states that it is impossible to create an exact copy of an unknown quantum state. This is a direct consequence of the linearity of quantum mechanics. It prevents eavesdroppers from intercepting quantum key distribution signals without being detected, because interception requires copying the quantum state, and copying is impossible without disturbing the original. The quantum revolution in technology is not coming. It is already here, in part, and its full impact is still unfolding. We have covered a century of quantum mechanics, from Planck's desperate trick with energy quanta, through Einstein's photon, Bohr's atom, de Broglie's matter waves, Heisenberg's uncertainty principle, Schrödinger's equation, the Copenhagen interpretation, superposition, entanglement, tunneling, many worlds, quantum field theory, and quantum computing. Let us now step back and look at what quantum mechanics tells us about the universe and where it is taking us. First, the accounting of what quantum mechanics explains. Every atom in the periodic table has the properties it has because of quantum mechanics. The reason hydrogen has 1 electron and helium has 2 and carbon has 6, and the reason these elements have different chemical properties is quantum mechanics. The reason solid matter is solid, the Pauli exclusion principle, which we have not had time to discuss in full, prevents 2 electrons from occupying the same quantum state, creating the effective impenetrability of matter, is quantum mechanics. The reason metals conduct electricity and insulators do not, band theory, a quantum mechanical description of electron states in crystals, is quantum mechanics. The reason semiconductors can be made to conduct or not conduct depending on the voltage applied, quantum mechanics. Every transistor, every microchip, every computational device ever built operates on quantum mechanical principles. The reason the sun shines, quantum tunneling and nuclear quantum mechanics, is quantum mechanics. The reason DNA maintains its double helix structure, quantum mechanical bonding, is quantum mechanics. The reason photosynthesis converts sunlight into chemical energy with such high efficiency, quantum coherence effects in the light harvesting complexes of plants, is quantum mechanics. The reason your eyes can detect single photons. The minimum detectable signal of light is 1 quantum, 1 photon, is quantum mechanics. Quantum mechanics is not a branch of physics that sits in a corner and applies to exotic systems in specialized laboratories. It is the foundation of everything. Chemistry is applied quantum mechanics. Materials science is applied quantum mechanics. Electronics is applied quantum mechanics. Molecular biology operates in a regime where quantum mechanics is essential. Now let us look forward. Quantum biology is an emerging field that is examining whether quantum effects play active roles in biological processes beyond those already established. The efficiency of photosynthesis has long been a puzzle. Plant light harvesting complexes convert sunlight to chemical energy with efficiencies approaching 100% at the molecular level. How do they route the excitation energy so efficiently from the antenna molecules where photons are absorbed to the reaction center where the energy is stored? In 2007, experiments by Graham Fleming's group at Berkeley detected what appeared to be quantum coherence effects in the energy transfer process. Wave-like oscillations that might allow the excitation to quantum mechanically sample multiple pathways simultaneously and take the most efficient route. The field is still debating whether these coherences are functional or coincidental. Whether the warm, wet, noisy biological environment, which destroys quantum coherence very rapidly, is actually harnessing quantum effects for functional advantage, or whether the coherences are just a byproduct of the molecular structure that do not matter for efficiency. This question remains open. But the fact that it is being asked seriously suggests that biology may have evolved to use quantum mechanics in ways we have not yet understood. The navigation of migratory birds is another area where quantum effects may play a functional role. European robins can detect the direction of Earth's magnetic field with extraordinary precision, using it to navigate on long migrations. The cryptochrome protein in their eyes appears to use a quantum mechanical process, a radical pair mechanism in which a photon creates a pair of molecules with entangled electron spins whose quantum mechanical behavior is sensitive to the local magnetic field, to detect the field direction. Evidence for this mechanism has accumulated over the last decade and is now quite strong, though not all aspects are settled. If birds are using quantum entanglement to navigate, then evolution has been building quantum devices for millions of years. Now, the deepest open questions. The first is the reconciliation of quantum mechanics with general relativity. At the smallest scales, at distances below what is called the Planck length, which is approximately 1.6 times 10 to the power of negative 35 meters. Quantum gravitational effects are expected to dominate. At this scale, the smooth space-time of general relativity presumably breaks down and is replaced by some quantum mechanical structure. What that structure is, we do not know. String theory proposes that the fundamental entities are not point particles, but one-dimensional strings, and that gravity arises naturally from string interactions. Loop quantum gravity proposes that space-time itself is discrete at the Planck scale, built from tiny quantum loops. Causal set theory, causal dynamical triangulation, asymptotic safety. These are other approaches with different philosophical and mathematical starting points. None has yet produced testable predictions that can be confronted with current experiment. This is the single most important unsolved problem in fundamental physics. The second great open question is the nature of dark matter and dark energy. Astronomical observations tell us that the visible baryonic matter described by the Standard Model constitutes only about 5% of the total energy content of the universe. Approximately 27% is dark matter, something that exerts gravitational influence on visible matter and shapes the large-scale structure of the universe, but does not interact electromagnetically and has never been directly detected in a laboratory. And approximately 68% is dark energy, something that is causing the expansion of the universe to accelerate, but whose nature is completely unknown. The leading candidate for dark energy is the cosmological constant, the energy density of empty space. Quantum field theory predicts that the vacuum should have an energy density due to virtual particle fluctuations. But the value that quantum field theory predicts is roughly 10 to the power of 120 times larger than the observed value of the cosmological constant. This is the worst quantitative prediction in the history of physics. The discrepancy between the quantum mechanical prediction and the observed value of dark energy is off by a factor of 1, followed by 120 zeros. Resolving this requires understanding something we fundamentally do not yet understand about either quantum mechanics, gravity, or both. The third open question is the origin of the arrow of time. The fundamental equations of quantum mechanics, like those of classical physics, are time-symmetric. They work equally well forward and backward in time. Yet we experience time as flowing in one direction. We remember the past, but not the future. Causes precede effects. Entropy increases. Hot things cool down, but cold things never spontaneously heat up. The origin of this asymmetry, the arrow of time, is not explained by quantum mechanics or any other branch of fundamental physics. It appears to be a consequence of the very low entropy initial conditions of the universe at the Big Bang. But why those initial conditions existed is itself unexplained. The fourth open question is perhaps the most philosophically provocative: the interpretation of quantum mechanics. We have already discussed several interpretations. The debate between them is not idle philosophy. Different interpretations give different answers to questions about the nature of reality, the meaning of probability, and the role of observers. Experiments in quantum foundations are becoming increasingly sophisticated. There are proposals for experiments that might distinguish between some interpretations, though designing and performing such experiments is very difficult. Some approaches to quantum gravity, if they produce different observational predictions depending on the interpretation, may eventually force the question. We do not know which interpretation is correct. We may not be able to know with current technology. But the question is not in principle beyond experimental reach. The fifth open question is whether quantum mechanics is the final story. Quantum mechanics has been tested to extraordinary precision and has never been falsified. But science does not prove theories, it tests them. Every test passed raises confidence, but does not guarantee that future tests will not reveal discrepancies. Newtonian mechanics was extraordinarily well tested for 2 centuries before quantum mechanics and relativity revealed its limitations. The limitations showed up at scales, atomic scales, relativistic speeds that Newton's contemporaries could not access. It is possible that quantum mechanics will show limitations at scales or in regimes that we cannot currently access. Perhaps at the Planck scale, the structure of quantum mechanics breaks down. Perhaps in the very early universe, when temperatures were high enough that quantum gravitational effects were dominant, the rules were different. Perhaps there are experimental signatures of physics beyond quantum mechanics that will eventually become accessible. We do not know. And the appropriate response to not knowing is not to pretend we know, but to keep asking, keep testing, and keep revising our picture of reality in response to what the universe tells us. That is what Planck did in 1900, when the blackbody data did not fit the classical theory. That is what Einstein did in 1905, when he took photons seriously despite their conflict with Maxwell's equations. That is what Bohr, Heisenberg, Schrödinger, Dirac, and dozens of others did in the 1920s when they built the mathematical structure of quantum mechanics from the ground up to match experimental reality, even when that structure violated every intuition they had inherited from classical physics. The lesson of quantum mechanics is not just the specific physics it contains. The lesson is what happened when physicists followed the data instead of their intuitions. The data led somewhere that no one could have predicted. Somewhere strange. Somewhere where objects do not have definite properties until they are measured. Where particles can tunnel through barriers they cannot classically cross. Where distant particles can be correlated in ways that cannot be explained by anything traveling between them. Where the universe may branch at every quantum event into multiple copies, each equally real. The universe did not ask our permission to be the strange. It just is this strange. And our only job is to figure out how. Let us end where we began. The chair you are sitting on is mostly empty space. The forces that make it feel solid are quantum mechanical. The atoms that compose it are stable because of the uncertainty principle. The chemical bonds holding those atoms together are quantum mechanical superpositions of electron states. Every photon of light reaching your eyes travels as a wave and arrives as a particle. The neurons firing in your brain are doing electrochemistry that depends on quantum tunneling and quantum mechanical bonding. You are a quantum mechanical object. Your existence depends on quantum mechanics at every level. And yet, quantum mechanics itself tells you that you cannot have a complete, classical, intuitive picture of what you are made of at the fundamental level. The atoms that make you up do not have definite positions and momenta simultaneously. The electrons in those atoms are not little balls orbiting nuclei like miniature planets. They are standing waves of probability, smeared over the entire atom. The photons that your eyes detect are not localized particles traveling along definite paths. They are excitations of a quantum field, existing in superposition until interaction selects an outcome. Quantum mechanics forces us to accept that reality at the fundamental level does not look like the world we experience at human scales. The classical world we experience is an emergent phenomenon, arising from quantum mechanics through the process of decoherence when quantum systems with vast numbers of degrees of freedom interact with each other. The classical world is real, but it is not fundamental. The quantum world is fundamental, and the quantum world does not have a simple intuitive picture. It has a precise mathematical structure. That structure makes extraordinarily accurate predictions about every experiment ever designed to test it. But what that structure means what it says about the nature of reality, about what exists when we are not looking, about whether there is a single universe or many, remains contested, debated, and unresolved. This is not a failure of science. This is science working exactly as it should, following the data, building the best mathematical theory to describe it, making predictions and testing them, and asking, always asking, what the theory is actually telling us about the world. The questions that remain at the frontier of quantum mechanics are among the deepest questions humans have ever asked. What is the nature of reality at the Planck scale? Why does measurement collapse the wave function? Is the wave function real, or is it a representation of knowledge? Is the universe deterministic or random at the fundamental level? Are there many worlds, or one? What is dark matter? What is dark energy? Can quantum mechanics be reconciled with general relativity? Is quantum mechanics the final theory, or will something deeper replace it as our ability to probe smaller scales improves? We do not know the answers. We know how to ask the questions precisely. We have the mathematics to frame them. And we have a century of experimental confirmation that the framework of quantum mechanics, whatever it ultimately means, is correct at the scales we can currently probe. That is a remarkable situation to be in. We have, in a century, gone from not knowing that atoms were real to having a theory of matter and energy that is accurate to 12 decimal places. From not knowing that light was quantized to having quantum computers that exploit superposition and entanglement to perform calculations no classical machine can match. From not knowing that particles could tunnel to having a world powered by nuclear energy and illuminated by lasers. From not knowing that distant particles could be entangled to building quantum communication networks that are secure against any known attack. All of that progress came from taking the data seriously and following where it led, even when it led to a place that overturned everything that came before. Quantum mechanics broke physics, and in breaking it, physics rebuilt itself into something incomparably more accurate, more powerful, and more honest about the nature of reality than what it replaced. That process is not finished. The questions at the frontier are harder than any that came before. The answers, when they come, will almost certainly be stranger than anyone currently expects. And that is exactly what makes it worth knowing.